Let me take one example to illustrate how to solve such kind of an optimization problem. So let me take an example here. So I will take one example from wireless communications. So what I want to do is I want to minimize minus of summation growing from I is equal to 1 to n log of alpha I plus xi, subject to the constraints that x is greater than equal to 0 and summation over xi, I goes from 1 to n, is equal to 1. Now you can draw parallel of this particular optimization problem with the communication system. Suppose you have, so you can write, suppose you have n communication channels, okay, and you have limited power. So your power is 1. So total power available with you is 1. Now what you want to do is you want to distribute this total power among these n communication channels such that your overall rate is maximized. So we want to maximize, this is the rate that you get from all the channels. So I want to maximize this. I made a minimization problem by using a minus sign here. Now how am I going to solve this problem? I'm going to write the KKT conditions here. So first KKT condition will be what? So before proceeding to that part, let me first check whether this is a convex optimization problem or not. So first step in solving such problem is to check whether it is a convex optimization problem or not. So let me see. So this is my function and these are the constraints here. Now the first thing is my function should be, or my objective function should be convex. So let me check. So here there is a summation log alpha I plus xi. Summation is from I is equal to 1 to n. Okay, so this is my function. Now so how am I going to check whether this is convex or not? I'm going to calculate the Hessian. So x is a vector, so I need a Hessian of this. So let me do the Hessian. Let me find out the Hessian. So I have to find out this Hessian of fx. Now you pause the video here and try to figure out the Hessian in your copies, and then once you are done, you again play the video to see how I have calculated the Hessian. Okay, let me now compute the Hessian part here. So the Hessian is, first I need to find out the derivative of fx with respect to xi. I'm doing it for xi. So this is going to be equal to, see, if I expand this function here, so if I expand this function here, I can write it as minus log alpha 1 plus x1 minus log alpha 2 plus x2 minus log alpha 3 plus x3 and so on. So if I take this with respect to xi, then these will be all 0 and only the xi log will be there. So that will be equal to minus 1 over alpha I plus x. Okay, so this is the first derivative, and if I want to find out the second derivative of this with respect to xi square, then it will be what? It will be alpha I plus xi whole square. Minus will go away and in the numerator it will be 1. Right? Can you verify that part for me? Right, so you are going to get this part, right? What about del square fx over del xi del xj? See, this one does not depend on xj, so this will be equal to 0. So the Hessian I can write, Hessian of this function fx, I can write it to be 1 over alpha 1 plus x1 square, then all zeros. These are all zeros. This one be 1 over alpha 2 plus x2 square and so on. Okay, only the diagonal elements will be there and the rest will be all zeros. Now is it a PSD, a positive semi-definite matrix? Yes. See rule 1. Okay, see rule 1, it will be very simple. This is in row echelon form and all pivots are greater than equal to 0. Alright, so from here we can say that my function, objective function fx is convex. Now let me turn back to the constraints here. The constraint here is, the first constraint is x is greater than equal to 0. It means actually that x1 is greater than equal to 0, x2 is greater than equal to 0 and so on. Okay, so what are my fi's? Fi's here, fi here will be fi x is x1 in this case, so this is f1x, f2x is x2 greater than equal to 0. Let me write it. Now you can do a similar exercise here also. If you take the Hessian of fi of x, then you are going to get a 0. Okay, you are going to get a 0 matrix. So this will be a 0 matrix. You can verify this very easily. These are all affine functions, so you whatever Hessian you are going to get, it will be 0, and this says that your function is also convex, rather it is a affine function, affine or a linear function. Similarly you can also, so this is a equality constraint and I said this has to be a linear function, and you can see this to be a linear function. So the first step I have completed. We have completed the first step of checking whether this is a convex optimization problem or not. Our objective is convex, our inequality constraints are convex, and our equality constraint is linear. Okay. Now the second step here is to write the KKT conditions. So step number 2 is write the KKT conditions. So how you are going to write the KKT conditions? The first one is going to be the constraints. So first one is the constraints. So x i's is greater than equal to 0. All i's going from 1 to n. So this is my first constraint. The second constraint is summation over x i's is equal to 1. The third one is lambda i's. So how many lambda i's will be there? There are n such inequality constraints. So there will be n such lambda i's, and lambda i's. So let me write a star. This is at the optimal point. Lambda i's are going to be, sorry, not equal to 0 but greater than equal to 0. For all i's going from 1 to again n. Now the fourth one is, see, I have to write it in the standard form. Okay, I should convert this into a standard form. So my standard form is, I'm writing here the standard form. The standard form is minimize f of x subject to fi of x is less than equal to 0 and hi of x is equal to 0. Okay, so here you can see the fi of x is less than equal to 0, so I should also convert this form into less than equal to 0. How I can do that is I can write it to be, so I'm writing it here, it to be minus of x1 is less than equal to 0, minus of x2 is less than equal to 0, and so on. Okay, so my fi of x are rather, my fi of x is rather minus x1 minus x2 and so on. Okay, so here my lambda I star xi star with a minus, this is equal to 0. I goes from again 1 to n, so minus does not make any sense, so I can very well remove it also, so it does not matter. And the fifth result is, if you take the Lagrange, then the derivative of my function f of x plus lambda I star derivative of fi of x star plus summation mu I of h of x star is equal to 0. Sorry, the derivative of this. And let me simplify this further. What will be the derivative of fx with respect to x? So this is going to be summation. So I'm doing it with respect to xi. So with respect to xi, what you're going to get here is, so if you recall from our earlier discussion, it is minus 1 over alpha I plus xi. So this becomes minus 1 over alpha I plus xi. This is a gradient. What is gradient of fi of x star? So fi of x is minus xi. So the gradient of fi of x at x star, this is equal to minus 1. Okay, so this will be minus lambda I star, right? And then what about this? My h of x is summation xi minus 1. Okay, again I have to convert this into the normal form. So this part I have to convert it into a normal form, and you can see it is here hix equal to 0. So I shift 1 to the other side, and this becomes summation xi minus 1. Okay, so if I take the derivative of hx with respect to xi, I get simply 1. Okay, so this becomes mu is equal to 0. There will be only one mu element because there is only one equality constraint. Okay, so these are all the equations that I have got here. Okay, and by solving all these equations, I can get the optimal value of xi stars. Okay, and I would like to you all to solve this problem in full, and please tell me the result of this problem, whatever you have got. So please send your results by Monday. Monday will be, the date is going to be 31st, sorry 30th. So you post your results on the Google Classroom, post on Google Classroom. So that's it for today. Let me do a quick recap of what we have discussed in today's class. So we started with looking at a convex optimization problem, why we are interested in a convex optimization problem. Then we discussed about what functions are convex. Then how do we prove that a particular function is convex? We have to prove the Hessian of the matrix to be positive semi-definite. And we talked about three methods. The first one is converting a matrix to a column to a row echelon form and checking the pivots. Then finding out the determinants of all the upper left submatrices. And the third method is if you have all the eigenvalues of the matrix to be positive, then the matrix is positive semi-definite. And then we showed you how to solve the convex optimization problem. You have to first prove that a problem is convex, and then you form something called as a Karush-Tucker conditions, KKT conditions. And then for a given problem, we took an example from a wireless communication system. And what you first need to do is we checked the problem to be convex, and then we formulated a KKT conditions. We got a set of conditions. Now after solving these conditions, we are going to get the optimal values of xi star. This I am giving you as a homework. You all guys please solve it and post your results on the Google Classroom, or you can also mail me. Or you can also mail me. Okay, you email me. Okay. So thank you very much. And in the next class, we'll do a recap of the detection theory and then we'll move forward. Okay, thank you so much.